Alright everybody, today we're going to be looking at two theorems, and these two theorems help make up our complex conjugate theorems. Our first theorem is your imaginary theorem, your imaginary root theorem, and your second theorem is your irrational root theorem. Alright, so recall that imaginary is represented by the letter I. Okay, and this is when you end up with a square root that has a negative radicand. So that would be part of your imaginary solutions. Okay. Your irrational roots, think way back to middle school. And probably a little bit of, maybe a little bit of freshman year too. Your irrational roots are roots that can not be written as a fraction, nor can it be written as a repeating or terminating decimal. Okay, something like pi. Pi is irrational. It keeps going on forever, but no pattern whatsoever. Okay. All right. Okay, so for the irrational, you're going to have a square root basically of a non-perfect square. Something like the square root of, I don't know, let's do 17. That would be an irrational answer. Okay. Alright, so most of these words you've seen already. You've seen complex, theorems, imaginary, irrational, roots. The one word you probably have not seen as of yet is conjugate. So before we can do any of the theorems, we need to understand what a conjugate is. Okay. Alright, a conjugate. Alright, now, of course, that's a formal definition, but I always like giving definitions where we can kind of understand what they're asking us to know. Alright, so conjugate is basically when you take the opposite sign of imaginary and irrational roots. Now we'll do an example like this in just a second so it gives you a little bit better understanding. Alright, when you have an imaginary root, they are in the form of a plus or minus bi. This a value right here is your real part of the solution, and this bi is your imaginary part of the solution. This is the part that you'll take the opposite of, because notice it says a plus or minus bi. It doesn't say plus or minus a, it says a plus or minus bi. So you're going to do the positive and the negative version. For irrational roots, it's going to be a plus or minus the square root. Okay. All right, and once again, the a is your real part of the solution, and the square root is your irrational part of your solution. So again, we're only going to take the positive and negative of the irrational part. Alright, so copy this down, and then we'll go through and find our conjugates of each one of these values. All right, let's take about 45 more seconds to finish copying this down. Now, as you're copying this down, remember how I talked about how roots, solutions, zeros, and x-intercepts all mean the same thing, and standardized testing likes to interchange those words to see if you're actually understanding the value of what the words mean. Well, they're going to expect you to know that if they give you that a problem that says the solution is 3i, they're going to expect you to know that the conjugate is also a solution. And we'll get to that theorem in just a second. But we first want to understand what a conjugate is. All right, well, speaking of understanding what a conjugate is, notice right here we have a positive 3i. Well, the conjugate is going to be a negative 3i. You have the positive and the negative version of an imaginary solution. All right, here we have negative square root of 7, so the conjugate is going to be positive square root of 7. Now notice both of these are monomials. We either have the imaginary part or we have the irrational part. We do not see the real part. The real parts are understood 0. That's the same thing right there as 0 plus 3i. But 0 plus 3i is still 3i, so that's why we don't write it as 0 plus 3i. Okay. All right, right here we have our binomials because each one has 2 terms. Okay. Now, again, remember I said that we only look at writing the conjugate of either the imaginary part or the irrational because it says positive negative of bi or positive negative square root. So right here for this one, we would have 5 instead of minus 2i, we would have a plus 2i. For our next one, the real part stays the same. We've got negative 11. Instead of a plus 4 times the square root of 3, we would have a minus 4 times the square root of 3. So again, notice the real part is staying exactly the same. And then finally for our last one, we've got 18 minus 8i. So our real part of 18 stays the same, but our imaginary part goes from a negative 8i to a positive 8i. So that's what the conjugate is. You take the opposite of the irrational or imaginary part. Alright, so for our theorem, the complex conjugate theorem. Now it's actually 2 theorems, but I'm going to combine them into one because they both say the same thing with just the one word difference. So this is your irrational root and your imaginary root theorems. All right, these theorems state if an irrational or imaginary number is a solution, then its conjugate is also a solution. Okay, so what does this mean? This means that if they tell you that 3i is a solution, you need to assume that negative 3i is also a solution. If they tell you that 5 plus 2i is a solution, you need to remember that 5 minus 2i is also a solution. They're not going to list both the positive and negative version of these irrational or imaginary numbers. They're going to assume that you know the theorem so that you know that the conjugate is also a solution. All right, as you're copying down example 1a, I want you to think about something about the conjugates. Can the conjugates ever be an odd number? Can you ever have an odd amount of conjugates? So you got the positive version and the negative version, or the negative version and the positive version. Negative version, positive version. No, you can't. They always travel in groups of two because you got the positive and the negative version. So they always travel in pairs. Okay, so the conjugates always travel in groups of two, so they're always in a pair. So if they're traveling in groups of two, that means you can never have an odd amount of complex numbers. It's always going to be an even amount. With that in mind, remember the complex is either the square root or imaginary, and they travel in pairs. See if I can spell pairs tonight. All right, so let's determine how many solutions we have to start with. Now we know, according to the FTA, the fundamental theorem of algebra, whatever your degree is of the polynomial, that's how many solutions you should have. So right here, my degree is 5, so I have a quintic here. So if all 5 of my solutions are rational, can any of them be complex? And the answer is no, because this column should add up to equal 5, the number of solutions. All right, for our complex, if we don't have any to start with, that's a 0. But can I have one complex answer? No, because again, they travel in groups of 2, so the smallest amount of complex answers I can have is 2. So if I got 2 of my solutions, 2 out of 5 are complex, how many are left to be rational? Well, 5 minus 2 is 3. So we still have a total of 5 solutions, but 3 are rational and 2 are complex. All right, we can't have 3 conjugates. So the next number we can have is 4. So if 4 out of my 5 solutions are complex, how many does that lead to be rational? Well, 5 minus 4 is 1. All right, 0, 2, 4. So then you kind of see the pattern here. What's the next? 6. For this one right here, can I have 6 complex solutions? No, because I'm only supposed to have 5 solutions, so 6 is too many. So I can now stop. All right, so let me give you one to try. Let's let this be a you try. Now, when I draw these columns, it doesn't mean that we're going to have that many. So I'm just drawing enough just to get some colors in there. So pause the video for about 1 minute and see what you get for me. Alright, so let's see how you did. Alright, so I see here my degree is 8, so that means I should have 8 solutions. If all 8 of my solutions are rational, that means I would have 0 complex. If I have 2 complex solutions, how many are left to be rational? Well, 8 minus 2 is 6. All right, then we have 4. So if 4 are complex, then 4 are going to be rational. If 6 are complex, 6 out of the 8 are complex, then only 2 can be rational. If all 8 are complex, well then that would leave none to be rational. Alright, so again, remember, anytime, if you need the video to be paused, if you're watching it dependently, pause it yourself. If you're watching it as a class, just ask the sub to pause the video for you to copy down anything that you may have missed. Alright, so here in example 2, they're asking us, would the given zeros find any missing roots and the degree? Alright, so I'll give you a chance to copy all those down, and then we'll work them together. Alright, about 45 more seconds. Okay, so here they give us some of our zeros, our solutions. They want to know, are there any missing solutions? And if there are, they want us to write those missing solutions and then tell the degree. So look at A. For A, did we see any irrational or imaginary solutions? Well, right here we can see that we got the square root of 11. So if we've got the positive square root of 11, then we know that we should also have its conjugate of negative square root of 11. So that means that we're going to have 1, 2, 3, 4 solutions, so we have a degree of 4. All right, for B, do we see any imaginary or irrational solutions? Well, yes, we do. We've got a positive 5i. So we have a positive 5i. So if we've got a positive 5i, then we also have a negative 5i. It's conjugate. So how many roots do we actually have here? 1, 2, 3. We have 3 solutions. All right, for C, are we missing any terms? Yes, we are. We've got a 3 minus 2 on the square root of 5. That's an irrational number. So if we've got a 3 minus 2 onto the square root of 5, then we also have a 3 plus 2 times the square root of 5. So we've got 1, 2 solutions. All right, for D. All right, 2/5 is rational, but 1 minus I is imaginary, so we should also have the 1 plus I. We've got 5 times the square root of 13. That's irrational, so if we've got the positive version, we should also have the negative version, negative 5 onto the square root of 13. So how many solutions do we have here? We have 1, 2, 3, 4, 5 solutions. All right, try E real quick. That's how you try. Give you about 30 seconds. All right, so let's see how you did. All right, obviously we see we got a imaginary here and imaginary here. Okay, so if we got the positive version, we should also have the negative version. But if you notice, these two right here are already conjugates. So we didn't have to list them again because they were already conjugates. So we only have 1, 2, 3 solutions right there. Yes, that one was a little tricky. And I made it tricky on purpose to see if you were paying attention. All right, finishing up with our last set of examples. All right, here in example 3. All right, we got write a polynomial function of least degree that have the given zeros. Now, these are going to have the same steps as we did the other day from the other lesson. The only thing that's different is that we're going to have to know that if they give us an imaginary or a rational, that its conjugate is also a solution. Alright, so for our first one right here, we see that we don't have any imaginary and nor do we have any irrational solutions. So we can just write all 3 of these in factor form. Okay, so factor form is going to be equal to, remember, x minus your root. So here we got x minus a negative 1, which gives us plus 1, times x minus a negative 2, which gives us plus 2, times x minus 3. Alright, so that is factored form. And remember I showed you how that you can verify this right here. You can put this in line 1 and then put, which is factor form, and then put your answer choices, which are going to be in standard form, and see which one gives you the same graph. Because if they are equivalent, the same inputs should give you the same outputs, so they will give you the same order pairs, which means the same graph. But we're going to work this out algebraically. So what we're going to do is we're going to FOIL it. We're going to FOIL these last two, and then we're going to use a distributive property right here with the x plus 1. All right, so I'm going to go ahead and bring down the x plus 1. All right, let's distribute. Let's use FOIL. Sorry about that. X times x is x squared. X times negative 3 is negative 3x. 2 times x is 2x. And 2 times negative 3 is negative 6. I'm going to combine like terms. So I have x plus 1. Negative 3 plus 2 is negative x minus 6. Okay, so I've got step 1. I got step 2. Now step 3 is to simplify, so that involves using a distributive property. So we'll come right here. I'm going to take this x. I'm going to multiply it times everything right here. X times x squared gives me x cubed. X times negative x gives me negative x squared. X times negative 6 gives me negative 6x. Alright, so I'm done with the x. Now I've got to multiply everything by 1. So 1 times x squared is 1x squared. 1 times negative x is negative x. And 1 times negative 6 is negative 6. Now, when you were taught to do the distributive property, you may have been taught to do the horizontal method where you wrote everything out horizontally and then combine like terms. But I like doing the vertical method where I line the like terms up. So here, f of x, when I combine my like terms, there's no other x cubed, so bring down the x cubed. Negative x plus x, negative x squared plus x squared, they cancel. Negative 6 minus 1 is negative 7. And then there's no other constants to bring that down. So this is my polynomial I get when I write this out. Now let's verify this. For this problem, are we trying to solve it, or are we trying to change it from one form to another form? Okay, we're trying to change it from factored form to standard form, so we're going to look for them to be the same graph. So let's put our factor form in. We've got x plus 1 times x plus 2 times x minus 3. Alright, now I'm going to put in my standard form in line 2. X cubed minus 7x minus 6. Alright, when I change it from one equation to one form to the other form, from factor form to standard form, do we see a different graph? And the answer is no. So that lets us know that these are equivalent, so my answer is correct. Alright, let's look at B. Alright, for B, I see that I've got a real number and an imaginary number. So since I got that imaginary number, if I've got a negative I, that lets me know I should also have a positive I as a solution. So we'll come right here, we're going to put this in factor form. Okay, so here we're going to have x minus 5, then x minus a negative I, which gives us plus I, and then x minus our positive I, which can give us a minus I. Now, in the other day we had the imaginary roots when we dealt with the quadratic formula, and we talked about how I is equal to the square root of negative 1. But then I said that we were going to save I squared into a later lesson, and this is going to be that later lesson. I squared, well, when we square a square root, we know that comes out as a negative 1. So I squared is negative 1, so keep that in mind. Okay, we're going to FOIL these two right here. So I've got x minus 5. I'm going to go ahead and bring that down. X times x is x squared. X times negative I is negative xi. I times x is a positive xi. And I times I is an I squared, and positive times negative is a negative. What do you notice is going to happen to these middle terms? Right, they cancel out because negative xi plus xi, they cancel out. So what we're left with is x minus 5 times x squared minus I squared. But what do we know I squared equals? I squared is equal to a negative 1. So what we really have right here is the negative of negative. Now normally I wouldn't write down all these steps, but I just want you to see what's going on. Negative of negative gives us a positive. And now we can FOIL this again. Yes, it's a lot of work. First two terms, x times x squared is x cubed. Outside terms, 1 times x is 1x. Inside terms, minus 5x squared. And last two terms, negative 5 times 1 is negative 5. Now, we changed it from factor form to standard form, but although we've done all our multiplication, adding, subtracting, etc., this is not in standard form because it's not descending order. So we've got to put it in descending order. My biggest exponent is 3. My next biggest exponent is squared, so 5x squared. Then the x to the first, and then our constant. So, all that. All right, so that's probably as complicated as you're going to get. Just remember if I, let me do maybe one more. Let's do a C. I don't have room to do a C, do I? See if I can squeeze it in right here, just to get you started. We won't work it all the way through. Let's say that we had the square root of 5 with a multiplicity of 2 and then a 3. All right, how would you start this? Well, we would start it by saying x minus 3 times x minus the square root of 5, and then x plus the square root of 5 because it has its conjugate. But here, since that's a positive, I would also have a negative, and it's being used twice. So that means these right here would be used twice. And I'm not going to make you multiply this all the way out, unless you just really want to. So again, the multiplicity of 2 means you would have x minus the square root of 5 squared. But if you have the negative version, then you also have the positive version, and vice versa. If you have the positive version, you also have the negative version, but it's also going to be used twice. So again, I'm not going to make you multiply that out. I'm just reminding you that when you have a multiplicity, that means it's being used that number of times. If that would have been a multiplicity of 7, you would have used that root 7 times, which means you would have used the conjugate 7 times. All right, we are done. So make sure you put your names on the notes, the date, and submit them.